Okay, we're right up to time, which is good because to maximize your value, we've squeezed 2 talks into this last slot. So we've got 2 10-minute slots, 2 10-minute talks. The first of those is by Tianyu Chen from CGG. Over to you.
Thank you. Before I start, I need to address some false information from Monday's plenary session. Firstly, CGG is not bankrupt. CGG is simply undertaking court-approved financial reconstruction process and continues business as usual. Secondly, it was incorrectly stated that CGG Airborne is for sale. It is not. As a matter of fact, CGG Airborne and Multiphysics are a core part of the CGG offering. The truth of the matter is that the CGG continues to invest in and develop improvements of the airborne technologies. And this is part of my core of my talk. Now, with that out of the way, we'll get into the presentation. First, I want to acknowledge my co-author, Mark Dransfield, for putting this together. Airborne gravity gradiometry survey, the advantage of that is obvious. It can acquire data over large areas cost effectively, efficiently, where the ground is not inaccessible. And also, it acquires data uniformly. And Falcon AGG system was designed and engineered specifically for this airborne platform, in that it is insensitive to turbulence, so that it allows the survey to be flown under turbulent conditions and also follow the terrains better. The CGG now has 6 systems, 3 the analog systems and 3 digital systems, and deployed on fixed-wing platform and helicopter platform. The helicopter platform system are digital because they are smaller, compact, can fit in a helicopter, inside a helicopter. The fixed-wing, of course, can allow you to cover large areas quite efficiently, and for the helicopter, you can fly low and slow, so you have a smaller target, you need higher spatial resolution, or you have a more rugged terrain, then helicopter AGG is the system to go. I'll go quickly to see over the years how the system has developed, has improved. From Monday plenary session, we know that the targets we seek seem to become more elusive and hard to detect. And this requires, because of geological signal, the geophysical signal they are generating are more subtler and weak. So this requires our system to be able to measure smaller and subtler signals that require the noise level to be lowered and also our bandwidth to be extended. Over the years, from the start, the first commercial survey of Falcon airborne gravity gradiometry system in 1999, over the years we've been working on improving the system. And the Falcon Plus is a system that with a half of the noise level of the standard Falcon system. And the full spectrum Falcon is a system that combines both the gravity gradiometry and the scalar gravity, so that we can acquire data, broadband gravity information from the air efficiently. And looking to the future, as David has mentioned, that CGG and Lockheed Martin are jointly developing the FDG Plus system. I'll just go very quickly over those developments. This is just a plot to illustrate the standard Falcon AGG, that's the topped curve, the noise floor, versus those the wavelengths we're looking at. FDG Plus is half at the noise floor. The resolution, spatial resolution of the system is determined by your line spacing and the filter you implied. For standard Falcon process, we usually for fixed wing, apply 300 meter filter length. But that for tighter line spacing, you lose some resolution to that. To address that problem, we developed the enhanced processing that takes advantage of the fact that along the survey lines, you collect data at a much higher sampling rate. So this enhanced processing allows us to extract the high frequency acquisition noise without impairing the high resolution geological signal we are seeking. So the next I'll show you just example we got from the Korean test set in West Australia. The image shows here are the vertical gravity gradient, or we call GDD image. On your left, that's the results from the standard processing. In the middle is the enhanced processing results. And on the right, that's the difference between the two. Compare the first two, the standard processing results and the enhanced processing. You can see the enhanced processing highlights more of the subtle features and more those spatial features of the geology are more finely defined or sharper. And the difference shows most of the difference between the two is along the line, that's acquisition noise. So this enhanced processing does indeed improve the data quality without impairing or losing much your geological information you're seeking. Another bonus is this process is the lower the noise level. For the standard processing, we're looking at, in this specific case, about 1.2 attwash square root kilometer. Well, with the enhanced processing, that was knocked down almost half. So this just to show you, with that enhanced processing, with tighter flight line spacing, you have a chance to increase your spatial resolution more. The long wavelength. Yesterday, I mean, Derek gave the talk, remember the Falcon, or in general, gravity gradient focus on the short wavelengths end of the spectrum of the gravity information we're seeking. And long wavelengths is also important because if you want a deeper, larger features, long wavelengths is crucial, the correct long wavelengths. It'll be ideal we can get both short and long wavelengths together. But there's ways, external ways, you can either get it from ground gravity, wherever it's possible, but the ground gravity, of course, suffers the deficiency of, it's not always available. And also the quality is available is a conglomerate of many, many years, even decades of data. You don't have a good grasp on the quality. And I need to rush through a little bit. And so, or you can get the satellite gravity is globally available, but it's not, doesn't have the frequency or the wavelength overlap we want. So you can acquire gravity separately, but that'll be more expensive. So it'll be ideal to get them together at the same time. So that's what we set out to do. For that to happen, your gravity system have to be small and compact and also robust enough to be able to survey the data with AGG system. So we select this S-graph system, which is a combination of the IMU system, differential GPS, and also the software that allows us to extract the gravity information. We test this system, which proves to be very efficient and offers very high quality gravity over the band up to a lot greater than 20 kilometer, 25 kilometer range that we need. So with that, the full spectrum Falcon allows you to measure both short and longer wavelengths gravity at the same time. Thus, it supplies the broadband gravity efficiently. So that's just to show with the longer gravity, you can have a better quality of the Falcon, full spectrum Falcon system. Quickly to the future, FG Plus, that's developed, now it's being developed by Lockheed Martin in cooperation with the CGG. It's a different design architecture. It has no rotating parts, and using air bearing, so that the expected performance is much better. Without the moving parts, without the demodulation necessity, we are able to expand the bandwidth to 5 hertz. And with the longer baseline and no moving parts, air bearing, all that, we're expecting the passband from 0.1 megahertz to 1.5 hertz. And so the expectation that sensor noise is so low is irrelevant. With that, I'll conclude the talk. That's another to show that different types of the system we're looking at. Thank you.
So we've got time for one question.
Yes. The question, I'll repeat the question. The question is the EFTG and FTG Plus, are they the same system? They're not. Yeah, they're not the same system.